I'm on software and the visualization team. Today, I'll give you a brief overview of a project that we announced back in February called Autonomy Visualization System, or AVS. In this talk, I'll cover these topics, the problems that AVS is trying to solve, why we're doing it, what it offers, and roadmap. Our jobs at Uber's visualization team is to turn numbers into visuals so that researchers, policymakers, and creators may gain better insights into the increasingly challenging urban mobility problem. Over the last 2 years, we have been partnering with the Advanced Technologies Group of Uber to develop Uber's vision for the future of driverless transportation. Together, we have been building a comprehensive solution for inspecting, debugging, and exploring information collected by autonomous vehicles during offline and online testing. Our self-driving cars and trucks are equipped with a rich suite of cameras and sensors. On the road, they see way more things than human drivers do, and they are capable of making decisions many times a second. For human engineers to understand why the self-driving car behave a certain way and further iterate on the software, they have to make sense of the context where these decisions were made. For those who are not familiar with this domain, let me take a minute to break this view down. So start from the top level, we first have the base map. That is the road network that connect the origin and the destination, the buildings, addresses, the satellite imagery, etc. These are essential for humans to make sense of the environment. Then we have the autonomous vehicle maps. These maps contain the every meticulous detail about the road. For example, where the lane boundaries are, is it a bus-only lane, is it a turn-only lane, what street signs and traffic lights control this lane, and where are they located. This information represents what a car knows about the road condition and restrictions prior to a trip. And on top of all of these maps, we have the vehicle log, which describes everything that's collected at runtime during the operation. In this screencast, you see the autonomous vehicle driving through an intersection with the front-facing dash cam, the bounding boxes of other vehicles and pedestrians on the road. All of them are moving and updating many times a second. Our design team have developed a special full set of abstract visual language to visualize this vehicle log. This is because the complexity of the vehicle log is 2 dimensions more than the map data. It doesn't just describe space, it also describes probability and time. There are 3 stages of algorithms run on top of the sensor data. We first have perception, which is what the car measures. For example, what objects are around us? Are they cars or pedestrians? How fast are they moving? We use color coding to show the classification of the objects on the road. At times, each object in the scene may have more than 1 bounding boxes if the algorithms consider alternative possibilities. And the perception engineers would want to see that. Then we have prediction, which is what the car forecasts. For example, is that car next to us going to turn into our lane? Where will it be 10 seconds from now? Note that predictions naturally describe possibilities of the future, and possibilities may change at any time given new information. This becomes a very interesting visualization design challenge, which is how do we illustrate something that are about the future, but that are only relevant to the present? So this is what they came up with. They draw a path from each object that is the projected trajectory and each dot along the path shows where that object is expected to be every 0.1 seconds. So now just by looking at the density of the dots, you're able to see how fast each object is moving and whether they're accelerating or decelerating. And similar to perception, the algorithm may consider there are several possible trajectories an object would take, and that is the multiple paths that's coming out of each one. At last, we have motion planning, which describes what the car decides to do. For example, are we changing lanes? Are we stopping at the next light? These are all reasonings that go into the car eventually pressing on the pedal or turning the wheel. A new can of worms, but something interesting here is we have this ghosted object, that we call look-ahead capsules, that we show where that object is expected to be at a future timestamp, and using those ghosted objects together with the planned trajectory of the vehicle, you're able to see whether that planned route is going to collide, for example, with some other vehicle. And if we're dealing with simulations, for example, there are also situations where engineers want to see what the car would have done given different circumstances. And that alternative reality is shown by a ghosted vehicle. And all of these things would be very overwhelming if we render them all together in one 3D scene. So all our applications offer the capability for the users to customize the view and turn on and off or change the styling options of all these objects to suit their needs. The tools that ATG needs are nothing like we've done before. When we first started working on this, it's even more challenging than it looks, because there's an overwhelming volume of sensor and log data that operators and engineers must see. You can easily gather more than 1 gigabyte of data in 10 seconds of log, and loading this information at near real-time speed and presenting them effectively is crucial to the productivity of the team. Working on cutting-edge technology also means that the feature requirements of these tools evolve every day. New hardware and new machine learning techniques may be employed, and the engineers expect to be able to see their new data and interact with their new data immediately in the tool. That means the specs of these applications change constantly, and it requires us to design something that can quickly adapt to new models. There's also a growing subdivision of disciplines, not just among teams inside a company, but also we also see it that new companies that are coming up that only deal with one small discipline of this entire workflow. For example, companies that just do map editing, do triaging, simulation, or labeling. Yeah, all of these companies require very tailored experiences and tools to address their own needs, and also calls for better collaboration, sharing, and even outsourcing support. Prior to AVS, we see a pattern in new self-driving initiatives. If you have a self-driving startup, most likely the first 20 engineers you hire, there's no front-end engineers. Most likely it's the autonomy engineer who put together some ad hoc visualization tool using off-the-shelf libraries, and these tools tend to be very inflexible, hard to maintain, and eventually fall apart as the team grows. This was that ad hoc tool that Uber used 2 years ago. At the time, it ran on a particular build of Linux and a particular configuration of hardware, and only worked on the office network because it was loading data off some disk array. It suffered from years of patches from researchers who desperately wanted to see their own thing. So as you can imagine, it has a steep learning curve and a lot of performance debt. When we designed our next generation solution, we did it with a web-first mindset. I think it might be unnecessary to preach to this room why web is more superior. There available on any computer from anywhere. This eventually allowed ATG to effectively grow the team and scale beyond Pittsburgh. The team was also able to bring in a lot of web engineers who are specialized in building good-looking, easy-to-use UI very effectively. It also allowed us to easily integrate with other web-based tools such as basemap tiles and task tracking systems. The outcome of this effort, AVS, is a new open standard for autonomy data visualization. It focuses on creating a consistent visual language across the disciplines for effective communication and decision-making. As we come to find out, although each company or team working in this space have their own special needs, there's a shared core set of problems that all need to solve. And AVS packages a solution for those core functionalities in an extensible way. By open sourcing AVS, we wish to break that vicious cycle of every shop strapping together their own ad hoc solution from scratch. Instead, we want to unite people in the field, empower them with the right tool that solves the right problem, incorporate the best ideas, and together build an ecosystem of compatible clients and services. AVS comes in two parts. The first part is a data protocol that's designed specifically for autonomy visualization called XVIS. Why don't we use some existing data format? Comparing to, say, game engine asset formats like GLTF, XVIS puts emphasis on autonomy, the autonomy audience, where it's very important to be able to introspect the data. It organizes data by semantic streams, associates geometries with objects, and allow for dynamic styling based on object properties. Comparing to widely used robotics formats such as ROS, XVIS decouples presentation from platform. Like a video recording, you can randomly seek and understand the state of the world at any time. The visualization layer can work across versions when new hardware and software components are continuously deployed. XVIS is optimized for efficiently transfer over the network. The encoding of data is aligned with what the GPU expects for 3D rendering so that we can minimize the client-side burden of data processing. Also comes with the server protocol so that the client can incrementally request more detailed information as the user inspects the data. In this demo, you see the user toggling different streams from a data set. An XVIS stream is basically a series of data updates that's associated with a timestamp, what we call primitives. In this video, the primitives here are LiDAR point clouds, camera images, object bounds, motion and prediction, motion planning and prediction trajectories, vehicle speed, etc. And each one can be individually turned off and on. Here's a diagram of how data flows from the autonomy system to the visualization client. AVS offers a component that build, validate, and encode source data into the XVIS protocol. The conversion can be done either offline so that you can store them statically and for future hosting, or at runtime on demand for a streaming service. On the client side, the data is decoded and synchronized into time-based data slices and eventually used for 3D rendering or building declarative UI components. Internally, we have multiple clients that understand the XVIS protocol, both on the desktop and in the browser. The open source Streetscape GL library is a web-based toolkit that makes consuming and working with XVIS data easy. We employ this what we call 80-20 philosophy. That is, we handle the hard problems out of the box, such as data buffering, coordinate transforms, 3D rendering, and interaction. This gets 80% of the app done. For the other 20% of your application, we do not dictate how data is represented or interacted with. Instead, we offer the building blocks and the customization capabilities so that you can tailor the app to your own user experience. This screen recording shows basically the out-of-the-box Streetscape React components come together in a web application. It shows a self-driving vehicle log in the real world and contains the 3D viewer, the 2D charts, video player, heads-up display, and playback control. All work together for a comprehensive end-to-end user experience. So demo time. So if you go to our website, avs.auto, we have a live demo using public data. This is a public data set called Kitty. It's shared by, I believe, University of Toronto research teams. And it shows a self-driving car going through an intersection. And you can see how it interacts and identifies all the other players in the street. And we can switch the camera modes to see from driver perspective or top-down view. And you can correlate what's happening in the 3D scene with a 2D charts on the side of the additional information. This is 10 frames per second, and every frame, I believe, is like 3 megs or so, 2 megs. Yeah, we're taking a subset of the point cloud, but internally we have much larger data sets that we were not allowed to put in a public website, unfortunately. I think typical frame is like 8 megs or so. On our website, we also have this tool that we call the XVIS Playground, where you can use live coding to pass your own data into the builder pipeline, see what it turns out to, and send it to the 3D renderer. For example, I will just manipulate that point and maybe make the object taller, different color, and you can see how things work. And this is used extensively throughout our documentation so people can understand how the protocol constructs the messages. So when building autonomy visualization software in the web, the biggest concern is always performance, performance, performance. AVS is built on top of years of investment that Uber Visualization has put in into WebGL-powered open source frameworks. These frameworks are designed for and battle tested with the over 100 internal products that powers the everyday business at Uber. The 3D rendering engine in Streetscape called WebGL is widely recognized as the state-of-the-art solution for geospatial visualization used by companies like Google, Microsoft, Facebook, and the like. WebGL grants us access to the power of the GPU while the CPU executes instructions at a higher speed. GPU allows us to performing repetitive jobs more efficiently by running them in parallel. If you think of visualization as a mathematical transformation of data from its bits representation to pixel representation, then dealing with a large amount of data is basically repeating that same transformation over and over again. And GPU is precisely designed for that. WebGL offers shader modules that perform common visualization transforms such as web Mercator projection. Here you see WebGL rendering almost 1 million geolocations as scatter plot at 60 frames per second. All that GPU is doing when you manipulate the map is recalculating the zoom level and the map center. Here you see WebGL performing data filtering on the fly. Here we are restyling 320,000 arcs based on where your pointer is. Again, the CPU is only sending the pointer position to the GPU, and GPU is doing all the heavy lifting of figuring out what to render and what to hide. This demo shows WebGL animating the position aggregating 4.5 million data points on the GPU. Here where when the user zooms or pans the map, it's recounting the data points that falls into any of the tens of thousands of grid cells on screen. And this can only be done efficiently using the GPU. This demo shows WebGL doing attribute transition on the GPU, so it's interpolating between two sets of point clouds dynamically. And you can do whatever you want with it. WebGL is the engine that powers the web client of AVS. I invite you to visit the vis.gl website and check out our live demos and documentations of the frameworks. Internally, Uber ATG's autonomous vehicle web platform is the foundation of a collection of web apps. The AV log viewer allows all of our operators and engineers to replay a log with base map, laser data, camera imagery, and everything that the car sees and thinks from any angle. The user can interact with any object in the 3D scene and to reveal more detailed information. For example, time series charts that show the velocity and acceleration over time for each object. And this is used to compare with the prediction that the autonomy software produced and figure out if something went wrong there. Triage operators rely on this to determine what happened in a particular takeover incident, and they can tag and assign tickets in the same UI. Autonomy engineers may also run a new version of their software in a simulation service, then compare its performance with the existing version by playing them side by side or on top of each other. In this case, it's showing that a bug has been fixed in the motion planner on the right in the new version of the software. This was especially important to the team last year when Uber halted street testing. ATG was able to continue iterating on its software offline. In the 4 months since we open sourced AVS, we got in touch with over a dozen companies working in the autonomy space and learned about each of their own use cases and special challenges. This screenshot is from Foresight AI, a company that built their 2D and 3D annotation products on top of AVS. We're committed to collaborate with the community and grow this ecosystem together. Very soon, we will exit beta and publish the 1.0 release. This version includes a stable version of the XVIS protocol, Node.js-based builder and server, feature complete web client components, a rollback to XVIS converter, and the interactive playground that you just saw. And right after the official release, we're also adding support for point cloud compression using Draco, new primitive types to address more use cases and continue to improve our examples and documentation. Internally, we have a C++ version pipeline that does converting and serving the data. It is our intention to eventually open source them as well, since C++ or Python are the more common languages used by autonomy engineers. For more information, look up our announcement post of AVS on Uber Eng blog or come talk to us. Thank you.